Let's talk differential equations, a little introduction for you. And if you want to print the sheet I'm using as the source of the notes and problems, you can go to bit.ly/diffeq-intro right here if you want to print that. So let's talk about differential equations. You often hear them abbreviated or see it abbreviated as DE or diffeq, but it is simply an equation that contains one derivative, so it's a very appropriate name. And these are four examples right here. You'll notice that each one of these have at least one. Some of them, like option B or B here, has two derivatives, y double prime and y prime. They do not have to have the original function. So some of these actually have y, which would be the original. Some of them don't, but they have to have at least one derivative. And even something as simple as d down here, where it's y prime equals 2x plus 7, you might look at that and not think differential equation. You may just say, hey, there's a derivative, and you could even find the function y by finding the antiderivative of that. But that does fit the definition of a differential equation. And the order of a differential equation is the highest derivative that you see in the equation itself. So option A right here, dy dx equals xy minus y, the highest derivative you see is the first derivative. So that is a first order differential equation. B, you see y double prime and y prime, so that is a second order. C, there is the second derivative, so that's a second order differential equation. And D, the highest derivative you see is the first, so that is a first order differential equation. And of course, they could be higher than second order. I just only put examples of first and second orders right here. So let's talk about one of the things that we're going to do with differential equations. Like algebraic equations, one of the things that we will do is find the actual solution to the equation. Now, on this sheet, I called it the ultimate objective. I don't know if that's really accurate because there are a lot of things you can do with differential equations, one of which is to find the solution. And the solution to a differential equation is the function that when you plug it into the diffeq and you plug in its derivatives, it makes the differential equation true. And so let's look at our algebra example here, 4x plus 8 equals 32. If I asked you to show me that x equals 6 is the solution to that, well, one option to show me that is to solve the equation yourself. So you could subtract 8 divided by 4 and show that x equals 6. However, let's pretend that this is like late elementary school and you don't know how to solve the equation yet. Well, what you could do if you don't know how to solve the equation, we're going to abandon that approach. We could just say, well, if they're telling me the solution, why don't I just plug in the 6 and see what happens? And so if I did 4 times 6 plus 8, that's supposed to equal 32. 4 times 6 is 24 plus 8 is 32. And you can show by simply substituting the solution in that it does make the equation true, and therefore that is a solution to that equation. Well, that's how we are going to start differential equations. I will give you a proposed solution. I will give you the differential equation, and you simply have to substitute it to show that it is the solution to that differential equation. So here we have y equals this quadratic, and we have this second order differential equation. And if it's a second order differential equation, I will have to find the second derivative. So let's go ahead and do that. So y prime, this is an easy derivative, 6x plus 6, and y double prime is going to be 6. And all we do, our first step, is simply to substitute everything in for the original equation. I'm going to substitute the original equation for y. For y prime, I'm going to substitute 6x plus 6. And for y double prime, we will substitute 6. And hopefully when we apply all the algebra to that, we will see that it is the solution to this differential equation. So 3x squared plus 6x minus 1 minus y prime, 6x plus 6 plus 3y double prime is 6. That's supposed to equal 3x squared plus 11. And now we just do all the algebra here. We're going to distribute combine like terms, 3x squared plus 6x minus 1 minus 6x minus 6 plus 18. 3x squared is by itself. I see a 6x and a negative 6x. Those cancel. And then I'm left with negative 1 minus 6 is negative 7 plus 18 is 11. And that was indeed what we were supposed to get. So we just showed that proposed solution did actually solve the differential equation, and that's where we are going to start. Eventually, you will learn techniques to generate the solution yourself, but right now we're simply going to verify proposed solutions. So I have a few other examples I wanted to look at. I think I have 4 here, and I'll go kind of quickly because some of these are going to be a little bit quick. I don't know. We'll see. Y double prime plus 4y. I already have the y. I need y double prime. So y prime, this is a chain rule. That's going to be 2 cosine 2x. Y double prime is negative 4 sine 2x. And so I'm going to substitute this in for the y double prime. I'm going to substitute the sine 2x in for the y. And let's see what we get. Y double prime is negative 4 sine 2x plus 4 times y, which is sine 2x. And you can see quite easily, hopefully, that negative 4 sine 2x plus 4 sine 2x is indeed 0. And so that is the solution to the differential equation. So they're not too bad, not too bad. First couple are really straightforward. I need y prime for number 2. This one's going to be even easier than the first one. Y prime is 2x. So when we substitute those in, 2 times y, x squared plus 10, minus x times y prime, which is 2x, is supposed to equal 20. 2x squared plus 20 minus x times 2x is 2x squared equals 20. Whoops, forgot my 2. And you end up with 20 equals 20. So therefore, we have shown that that is a solution to the differential equation. Now, those two are kind of straightforward. Let's look at a little bit trickier one. Lots of unknown constants in this one. We have y equals a plus c e to the kt. Now, do remember that a, c, and k are constants, and e obviously is a constant as well, 2.7182818284590452353. So we need the derivative, and I need the function itself. So the derivative of y, dy dt, is 0. The derivative of a is 0 plus ce to the kt, and the derivative of ce to the kt, I'll just bring the c along for the ride. The derivative of e to the kt is e to the kt times k. It's a chain rule, so I could call that ck times e to the kt. And let's substitute that and see what happens. So dy dt, I just found that. C times k times e to the kt equals k times y, which is a plus c e to the kt minus a. And if we start cleaning that up, this one falls into place very quickly. A minus a is 0. Distribute that k, or really it's not even distributing anymore. It's k times that. And we end up with c k e to the kt is equal to k times c, which is ck e to the kt. And we're done. We have verified that proposed solution. We have one more. I'm jumping to number 6 on that sheet that I gave you earlier. Find all the values of a that make this a solution to that differential equation. Now, the structure of this is very similar to the second example we did, where it was like sine of 2x was your function. So I have y, which will go in place of y. I need the second derivative. So my first derivative, dy dt, is going to be negative sine at times a. So negative a sine at. And the second derivative, which is what I need for the diffie q given, would be negative a squared cosine of at. And now we're going to start substituting. Negative a squared cosine at will go here, and I'll plug the y in for the y in the equation. So we have negative a squared cosine at plus 9 times y, which is cosine at. And that needs to equal 0. And I think I want to solve this one by factoring. I'm going to factor out the cosine at. And when I do that, I'm left with negative a squared plus 9, which is also 9 minus a squared. My parentheses and brackets are all over the place. There we go. And so we need cosine of at times 3 plus a times 3 minus a to equal 0. Oh, this is kind of an interesting problem. I did not anticipate this happening. A poorly written, maybe not poorly written problem. You will see the issue here in a second if you don't already. Easy solutions are a equals negative 3 and a equals 3. And I think when I wrote the problem, those were the two I was thinking about. However, it is possible that cosine of at equals 0 and cosine is equal to 0 when the angle is equal to pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth, which can be generalized as AT equals 2n plus 1 times pi over 2. And that would give you, start plugging in numbers for n. If you start plugging in 0, you will get all of your odd multiples of pi over 2, which means for that cosine function, t could also equal 2n plus 1 times pi divided by, whoops, I'm solving for the wrong thing. Find all the values of a. Oh goodness, we're solving for a. So a would equal, I'm having a hard time here. A would equal all that stuff divided by 2t. So it really depends on what t is for the value of a for that second one. So that last one was kind of weird because it's dependent on the value of t. However, 3 and -3 would always be values of a that make that a solution. So there we are. Number 6 did get a little bit wonky, but that's all I want to do with this right now.